Next, we're going to apply the CLT to a distribution where the parent distribution does not begin as being normal. So in this example, it says, according to one very large study done in the US, the mean resting pulse rate, so we're talking about means here, the mean resting pulse rate of adult women is about 74 beats per minute with a standard deviation of 13. So this is about all women. So it looks like this is my mu, this is my sigma. But what's interesting here is it says the distribution of resting pulse rates is known to be skewed right. So this does not start off being normally distributed. Something that looks like this. Most people have a fairly, low resting pulse rate with some that are higher. It can't go much lower, otherwise you're dead. So it says, suppose we take a random sample of 36 women from this population. 36 is my sample size, which is greater than or equal to 25. The only reason I can proceed with this question, because the original was not normal, I needed my sample size to at least be 25. It is, which means I can proceed and use the normal calculator. We want to find what's the approximate probability that the average pulse rate of this sample will be between 71 and 77 beats per minute. Okay, so we are allowed to use the normal calculator because we checked our condition. The mean should be the same as the original mean of the whole population, so the mean is still 74, but we have to calculate out that standard error. So let's figure out what are we going to put in for that. We take the original standard deviation of 13, divide that by the square root of 36. So 13 divided by 6, which is approximately 2.17. That's what goes up here. Because again, we took a larger sample, a sample of 36, so that's going to bring that standard error in from the standard deviation. It was 13, now it's only 2.17. And we're going to find the probability of being, this is another between, we want to be between 71 and 77 beats per minute. So let's switch over to our normal calculator now with this information. If we have a mean of 74, standard deviation of 2.17, find the probability of being between 71 and 77, compute. Looks like 83.3%. So either 0.883 or 88.3%, however they ask you to give that answer back. And that's whichever one of those can be your final answer. So that's your probability that out of these 36 women, if you were to pick just randomly 36 women out of of all US women, average up their resting pulse rate, there's an 88% likelihood that it will be between 71 and 77 beats per minute. Then it says, can you find the probability that a single adult woman will have a resting pulse rate less than 3 beats per minute away from this? So can I do the same thing in this scenario, but do it only for a single woman, for one person? I go take one random woman, and can I calculate the probability that her resting pulse rate is between these two values? And the answer here is no. Because a sample size of 1 is not less than or not greater than 25. The original population distribution is not normal, right? It was right skewed. And the sample size is too small. So we fail condition 2. In the CLT. That means we are not allowed to apply the normal calculator here, and we are not able to proceed finding that probability. So do be very careful when you're doing your questions in MLP. If it tells you in the problem that the original distribution, the original population is normal, you are good to go. If it doesn't, or if it tells you flat out that it's skewed one way or another, then you have to make sure you hit that 25 sample size, otherwise you cannot proceed. Okay, so let's see. Let's just kind of review. The population distribution is the distribution for the whole population. And for some populations, we don't even know what it looks like. So we knew that the women's resting pulse rates were right skewed in some way. But a lot of populations, I don't know what they look like. They could be anything. They could be multimodal or skewed or anything. Now the samples, though, what we do know about them is that if the sample is truly random and large enough, then the sample should be representative of the whole population. It will look similar but not the same as the population distribution. So it will start to look different. You know, you have some questions like this in your homework where it gives you some images of some distributions and asks you which one is the population, which one is a sample of a certain size versus a sample of another size. So on this one, we want to say which one of these would be the original population, which one would be a sample size of 10, and which one would be a sample size of 25, and explain why which is which. So again, the craziest looking ones are going to be your populations. They can look any which way, and sometimes we don't even know what they look like. So that will the craziest one will always end up being your population. Now, if we were to take random samples from this, drop them down right, make that distribution of means, what should happen is that as our sample size increases, it should start to look more and more like a normal curve, and its standard error should come in. So these both, my A and my C, both look fairly, quote, normal. They look unimodal and pretty symmetric. So the way I'm going to tell them apart is their standard errors. The one with the smaller standard error should be the bigger sample size. So it looks like I would label this one sample size 10 because it's got, from its mean, it's got kind of more spread, a larger standard error than this one. This one looks like that standard error, that plus minus amount is coming in, forcing it kind of up higher. So this one is what I would choose as my 25 sample. That's going to have the smaller standard error. So you can see why you have to get a population, you have to get a sample that's big enough that it truly is going to look normal and truly is going to have a nice small standard error so that our normal calculator will work. So as increases, the sample distribution, just to summarize what I've been saying, should look more normal in shape with a smaller standard error.